All right. There's problem number 8 and then a problem number 9, and they're pretty similar problems. I'm kind of hoping that we can do number 8 together, and then you can do number 9 with a little less help. And I'm just going to review what we did, because we did this a few classes ago. This is a student who's starting from rest and then running up the hill. So at the beginning, they're not moving, and up here, they are moving. And we could do a graph of this showing potential energy, kinetic energy, other energy, and I think you'd be able to do that. But to solve this problem, we've got to think about this in terms of extra work that gets done on the system. So in the beginning, we found the kinetic and potential energy just using the formulas. Kinetic energy is 1/2 mv squared. So 1/2 times their mass is 70 times the velocity. Oh, so this is the final velocity. Final velocity is 5 meters per second, it says, and that's squared, so that's 875 joules. So they have 875 joules of kinetic energy there. And in the beginning, they didn't have any potential energy because they didn't have any height. But at the end, their mass is 70, here's G, and here's H. So multiplied together, that's 4,116 joules. So they're going from, in the beginning, 0 potential energy plus 0 kinetic energy. So the total mechanical energy is 0. And in the end, they have 4,116 joules of potential and 875 joules of kinetic. And if you add those up, you get 4,991. And that has to equal the work that was done on the system. So the work that is done gave them that energy because they had no energy in the beginning. So this is asking to use the work formula to calculate the average force exerted by the student. And work is force times distance, and we know the work, so we can plug it in right there, 4,991 divided by distance, and we can get that force. And now we're going to find power. So you probably don't remember this, but the power formula is work divided by time. So work over time. And the amount of work, I want to see if people are paying attention, so I'm going to ask one of you how much work there was. Crow, how much work was there?
Wait, 4,900.
4,991 joules. That's the amount of work that was done on the person.
Yeah.
So I can write 4,991 joules, and the time it says is 4 seconds. So if I divide 4,991 by 4, get the answer. So 1,200, I'm just going to round, 50 watts. And you don't have to do this, but I just think it's kind of interesting. If I take 1,250 watts and I try to convert it to horsepower, 1 horsepower is 746 watts. So I just need to divide this by 746, and it's about 1.7 horsepower. So if you did this, if you were a 70 kilogram student, which would be somewhere around 150 pounds, and you ran up a ramp that was 20 meters long, and you did this in 4 seconds, and you gained 6 meters, you would have to exert 1.7 horsepower constantly in order to do that. All right, flip to this. Now we've got a rock climber, and you're going to need a calculator to do this, so I'll bring calculators around. Get yours out if you need to. Students on the ground level, and they're not moving. It's a 90 kilogram student. Maybe they're wearing a harness, or maybe they're just big. And at time 0, they're going to start to climb up here, and at 16 seconds, they're going to be right here, and they're going to be moving at 0.7 meters per second. So this says to find the starting and ending kinetic energy and potential energy. If you don't need a calculator, just tell me. So the formulas, if you need formulas in your handout, they should be back on page 5. There's the kinetic energy formula for number 1, and the potential energy formula is number 3. And when we get to power, the power formula is down in number 7. Some of these are easy though. I'm going to write PE0, KE0, PE, and KE. Of those 4, which 2 are the easy ones? Because there aren't any. Which ones are 0? Initial. So when they're right here, there's no velocity, so the kinetic energy is 0. And they don't have any height, so the potential energy is 0. But they do have potential energy and kinetic energy there, so try to find that. You'll need a calculator. We're on page 7. I'll freeze mine and do the work. So I think we'll probably have a little quiz next class like this. Oh, and for G, use 9.8. Ooh. Do you have the handout?
No.
You sure?
Yeah.
Looks like we got it a few days ago.
I don't think I have it.
Well, take a look and see if you have it. It was a while back. We haven't done anything with it in a while. What do you have? Yeah, I was disappointed in that. I should have made it going faster. The kinetic energy, there is some at the top. The kinetic energy is small. If you came up with a number and you thought, that seems ridiculous, you're right. No, shit, I got 22. Yeah, check that again. 22 plus 1 or something. Okay, so some of you are looking stuck. here's my work. The formula for potential energy is mgh. So you just get the mass of the person, and g is 9.8, and then the height is 10, and if you multiply all three of those things together, this times this times this, then you get 8,820, and the unit should be joules. This one, kinetic energy, it's a little bit more trouble, but not that much. So I'm going to type in 0.5 first times 90, that's the mass, times 0.7, and then I just like to use this little squared thing on here, squared. So 22.05, I just called it 22.1. It's kind of negligible. The kinetic energy is really small compared to the potential energy. So step 2 says to use the law of conservation of energy to find the work that was done by the student. You don't really need the law of conservation of energy to do this. So in the beginning, how much energy did they have altogether? 0. In the end, they had all this. Guess how much work was done? All of that. So I'm just going to write it out mathematically. This is the law of conservation of energy. So PE initial plus KE initial plus whatever work is done equals PE final plus KE final. This is just saying the total energy in the end and the total energy in the beginning, they're the same, but if they are different, it's because of either energy that's added or taken out. In this case, it's going to be added because we had 0 potential energy, we had 0 kinetic energy. So all we've got is whatever work was done by the student. And then in the end, there's 8,820 joules of potential plus 22.1 joules of kinetic, which is, so I can write the work done is, well, I can do that in my head, 8,840.1. I'm just going to round it to 8,840 joules. So that's how much work was done. Step 3 tells us to use the work formula to calculate the force. So the work is force times distance. And you can either use standard algebra to solve this one, or you can use just make the triangle and solve it. So try that. I'm going to do it too. Good. Can't find it. Good. I haven't done that yet.
So I was looking in my cover scroll and my grade didn't change for the test. No, I got
Oh, no.
17 to 17. No, this is a different one, but that was from 12-4.
Can you remind me right after we're done with this? I don't want it to show up in the video. All right, here's the reveal. You should have 884 newtons. So if work is force times distance, this is the work. There's the force, there's the distance, 10 meters. So you could do it like this. If you have 8840 equals F times 10, divide both sides by 10. 8840 divided by 10 is 884. If you wanted to not think about doing the same thing to both sides of the equation, you could just put this in the triangle like that. And if we're solving for force, then it's just work divided by distance. 8840 divided by 10. Okay, so now the power formula to calculate the power in watts. And you don't have to do number 5. You don't have to convert it to horsepower. Oh, by the way, that 884 newtons is about 198 pounds. So this climber, it's a pretty hefty climber, 90 kilograms is a lot of mass, would have to exert a constant force of 884 newtons or 198 pounds in order to do this. The power formula, again, is back on page 5, but power is work divided by time. And that should be pretty quick. I'll give you just a second to do it before I do it. Okay, I'm going to do it. The work is 8,840 joules. And the time, looking back to the question, is 16 seconds. And joules per second is watts. So about 553. And you don't have to do this conversion, but if you want to, 553 watts converted to horsepower. We want to have watts cancel. We want horsepower in the end. 1 horsepower is 746 watts. So to make this work out, I just need to divide 553 by 746. So this is only 0.74 horsepower. And that's it. So expect a quiz next class over something just like one of these. You'll have steps 1, 2, 3, and 4, but not 5. You don't have to convert to horsepower. Actually, I might make that a little bonus point. So do you want to do one more practice or just call it good? Another one?